You tried that?
Forgot to do it.
Okay, so let's do it here also in class as I promised. So this is a very simple problem, but it's important to go through it. So basically we have so this opening we need to find out, because that's what we will have on our mask design, and this distance which is given, which is 450 micrometer, and this distance which we want at the end is 350 micrometer. So one thing, in order to solve these kind of problems, and there was two things given. One was angle, right? So this was 54.7 degrees, and the etching rate in this direction, which is 100, it was 0.6, I believe, micrometer per minute for TMH at 70. I don't know, I didn't give the temperature. I think it was 20%. There was 90 degrees centigrade. So, and then there was a etching rate in that direction, in this plane, which is 111, and this was 0.027, I believe, micrometer per minute. So these are the things which were given to you at the start, and now the question was how we can calculate how much would be our starting window. So any of these problems, any of these kind of problems, you should use just a regular trigonometry to solve it at the start. So for example, in this case, we can just draw a rectangle here, right? Okay, this is not symmetric, but in reality it is symmetric. So how much would be then this distance from this point to that point? 350, right? Because I'm making a rectangle. So this 350, so one dimension I know is the 350 plus something on both sides, okay? So we can calculate on one side because it's symmetric, so we can find out the other side. So at one side, if we look at this triangle, so it looks like I'm just redraw it, 54.7, and this is the perpendicular, this is the base, this is hypotenuse, right? Okay, I can use sine theta or cos theta, and the formulas involves the perpendicular and hypotenuse and base and hypotenuse, right? But then we don't have, actually, we have a perpendicular, but we can find a hypotenuse from there, and by using maybe another question, we may be able to go back to base if we have both perpendicular and hypotenuse, right? We can find the third one. That's the one way, but a little bit difficult, a long way, I would say. The most straightforward is when we want to find this B, which is base, and we have a perpendicular which is given, which is 450 in this case, right? So we can just do tan theta is equal to perpendicular over base, right? That means 450 micrometer over base, which we want to find, and so it means we can write base is equal to 450 over tan theta, correct? So how much is the value for tan theta? Do you have calculators? You said 900 something?
987.
Okay.
Yeah, I just started. Micrometer.
So, anyone who has a calculator? Huh? 3.6? You said 450 divided by 3.6?
10, 54.7. So I got like 318.
318.6. Let's say 318 for example. So can you divide 450 divided by 318? 1.42. So if it is 1.41 or 1.4?
1.41.
1.41. Okay. So let's say we have 350 and then 1.41 at one side plus 1.41 on the other side, right?
No, like
No.
the 318.
Just the tangent.
Yeah, the 318 was 450 divided by tangent of 54.7.
That is 318.
Oh, the whole thing was 318?
Mm-hmm.
18.6,
6.
6, yeah.
okay.
And 10, 54 is
1.41. Okay. So we got 318.6. Okay, let's see. Whew. So how much this total would be?
987.2.
987.2.
Yeah.
Okay, by the way, when we solve any problems which are trigonometric related, do we use angle in theta or radians when we go with tan and sine? No, theta, we use
Or degrees.
In this case, it's degrees, right?
no, I'm asking you, yeah. You're asking me, no.
It depends how you set your
Since you set it up
You're
for
gonna set it
degrees, I made sure to make degrees.
No, I gave value in degrees. It doesn't mean that we really have to use the value in degree, right?
You could convert it to radians.
We can. Do we need to? Because it will.
Not in this case.
Can you, Kabir, you have a calculator, right? So can you find out, I think if theta is 54.7, okay, and how much would it be in radian? I think 0.95 approximately. Radians, okay. And now can you calculate tangent of 0.95 radians?
$1.398.
1.4. And can you divide now 450 divided by 1.4?
321. 321.
321. 450 divided by
1.4.
321.
21.
It's very close.
No, it's the same, but it's the same result.
But why? Okay.
No,
Because
it's
the
no,
estimation,
yeah.
since you estimated.
No, maybe they took out some decimals, but if you do it real sharp, it will give you the same result.
Okay. But I thought it could be a different number.
No, it's the same one. Should be.
Okay. So it means it doesn't matter, but it should matter because of what skill we're using. So, okay. So can you do again, Kabir? Tan 54.7. Is it still 1.41 in degrees?
1.41.
Okay, then it's the same number. It doesn't matter if we use a radian or degrees in this case. So our answer would be 987.2, right? That's your starting window. But I also gave you that it is etching in 111 direction, right, on the sides also. And we have not accounted that, or do we have to account that in designing our mask? Because if it's on the sides, it means maybe it's also etching on this side, right? And also on this side. So from where we started, at the end, maybe after 1 hour, 2 hours, it's a long process normally. Can you tell me, okay, before that, can you tell me how much time it would take? Okay, now we design, like say, our mask, which is a 987. And someone got a different number, right? But how come, but he's giving same answer, how come you got a different number then?
It's when you switch your calculator.
Okay, so calculator issue?
Yeah, so you have to make sure if you're using radians to make sure you calculate some radians. If you don't switch it, then it'll give you a completely different number.
Okay, Kabir, when you're calculating tan 54.7, is it radians or 80 degrees, right? And when you calculate tan, okay, that's fine, but then I don't know. But anyways, but there are also etching on the other side, right? So by the way, question is how much time it will take. Okay, now we have our mask, we design it, we print it in the photolithography, and now it's on our silicon dioxide, and now we have to put it in a etchant, which is a TMH in this case, to make this structure, right? So should we leave it there forever, or should we do etching for some time? How we calculate how long do we have to do etching in order to achieve this kind of a structure? Can you calculate how long we have to do etching?
Divided by 0.6.
Divided by 0.6. Dividing what?
The full amount of 987 divided by 0.6.
987, which is 450 divided by 0.6, because in this direction this is 0.6, right? So we have to go 450 micrometer. So 450 divided by 0.6 would be how much? Can you calculate? So total time it will 450 divided by 0.6. You said 750 minutes, right? And you can convert it into hours by yourself. Okay, that's important information. So it means now we know, okay, we have to put it in for that much period of time, and we have a structure like that, but during that time it will also be etching this way, right? So it's not, because it's etching this direction, 0.027 micrometer per minute. So then at the end, let's say we started from here, then at the end we will have this structure like that. So basically how it etches, the next, if I etch it a little bit longer, so the next structure would be something like this. Okay, the angle will still stay the same, but again, it has to go that way. Otherwise, how you can achieve that structure, right? So if it go that way also, then how we can calculate how much it would have etched on sides? I gave you etching rate, by the way, which you didn't use. None of you, it looks like.
Divide the past 350
Yeah,
one side by 0.027.
Point 027. So what numbers? Can you tell me numbers? What divided by what?
318
318.
divided by 0.027.
318 divided by 0.027. No, I don't think it's right. So in exam I can ask actually any question regarding all this. It can be finding out this side, that side, time, and like around these numbers. So make sure we are understanding everything.
Now you use the 0.027 because you should, it goes in that direction.
0.07? What?
0.027 micrometers.
Oh, that's a give.
Direction 111.
111 direction is.
Yeah, you have to estimate like difference.
I didn't get your point.
But you have a ray going that way.
Yes. Think about it. Let's say if we started this one, right, and this window is getting closed, okay, and then later on we can go deep this way, right, and then it can close at some point. This is how it works. But it's also etching that way.
Yeah. At the same time.
At the same time, yes,
Yeah,
yes. So it's not a. Otherwise, it would have been a straight wall. But it's also etching that side So it means it will also be etched on this side based on that etching rate. Yes?
We're trying to find how far it'll go.
Yeah, because let's say at the final, so we want this window to be, for example, we want this window to be 350, right? So for 350, we calculated our starting window will be 987, right? And we also want it to 450 micrometer deep. So if we start with 987, we will not end up actually getting 350. That I can tell you.
Then it would be.
Because it will also be etching both ways.
Yeah.
So at the end, the structure would be something like this. Okay, because you'll be etching. So then at that time when you look at your windows, this window will be 987 plus something more. Because you're etching on the sides also. It's not going only downwards. And that rate I gave you, 0.027 per minute. That's how it's etching on the side.
Yeah, but if you take like 750 minutes, you will achieve the vertical.
Yes.
In the 750 minutes, you will achieve 0.027 multiplied by 750, you will achieve, well, that is 20.
That's correct.
Then it will be smaller.
Yes. That's correct. Yeah, that's what my question was.
Oh, no. I was wondering how to make it that size.
Yeah, so basically what you have to do is we have to include that 0.27 micrometer per minute, let's say, for how long we are etching? 750 minutes, right? So in 750 minutes, calculate how much it will etch on the side. So 750 into 0.27, can you do that? Anyone?
Yeah, about 20.25.
20.25, right? So it means 20, let's say 20 micrometer, it will etch on the side in 750 minutes. And one side, and both sides it will be 40. Okay, 40 micrometer. So it means 987 minus 40, or let's say 987 minus 40, it will give you 947. So if you start with 947, you should be ended up getting actually this structure at the end. Right? Okay, I hope everyone got the point.
Sorry, it should not be getting 350 plus 40.
350 plus 40? No. No, we should not be getting that.
It will be going like this, and after it will be...
No, it'll go always like that.
Oh, it's like that?
Yeah, it's always. When let's say if we have a window, let me make another window. Okay. Okay, let's say this is silicon, which we're etching, and this is silicon dioxide, okay? If we put this in if we put this structure in a TMH or QH, so what will happen? It will not start etching like that. It will go this way with that angle. So one time it will make us maybe this structure, then it will make that structure, it will make that structure, so in that way it goes. So the question can be asked, for example, I may give you the starting window, let's say 300 micrometer. I may give you this window, and I ask you after this much time how the structure should look like. You may have to draw the structure. So if I give you starting window and I tell you, okay, after 2 hours how this look like after etching, how the profile should look like. So you should be able to calculate that, right? You know the angle already. You know how much deep it will go. I will give you etching rates. So you should be able to draw the structure. And what happens sometime in this window, I can give you structure also like this. Because it can close. Based on if you start with a small window, then it will close at some point. So when it closes, I can ask you, okay, if it is going that way, so after how long it can close? Right? So, and everything has to do like programmatically. It's not very difficult if you understand how it goes. So when it's closing, it means in that case you don't have this part. Right? So then you only have to calculate actually these two triangles. You should be able to find the starting point, right? So I'll leave you with that note. Try one more time at home if you want to. If you still have questions, we can discuss. Okay, so let's move on. In etching, so this TMH based anisotropic etching. By the way, the TMH etching is the isotropic or anisotropic? Who says it's isotropic? Anyone? Who says it's anisotropic? Almost 60% of people, so it's fine. so it's anisotropic because it's etching in one direction more than the other one, and that's why we also want to go through crystal structures. I think we didn't discuss in the class, but there was a lecture which I uploaded. So where we briefly talk about the crystal structures and give you an idea of when I say 100, what does it mean? So at least now you know, okay, 100 means the crystal structure in certain direction, in X direction or Y direction, right? So that was the whole goal to give you some background on crystal structures. But some structures are very complicated, like the silicon structure itself is also complicated. It's not very straightforward. It's a double diamond, and there are about 16, I think, atoms involved in one crystal unit. So the structure itself is very hard to draw. I cannot draw it still on a paper because it's in 3D. Some atoms are in the middle, some are actually inside the cube. So if you look at it online, you will find it's a little bit complicated. But yes, it is a crystal, double diamond crystal, the silicon itself. Okay, so sometimes we want to achieve a high aspect ratio features for a certain reason. One way can be anisotropic etching, where you can go much deeper inside. But sometimes we want the straight walls, the vertical walls, for a certain reason. In this case, the walls will be pyramid shaped with the slopes. We don't want that. So we want walls to straight, most probably, and deep. Let's say I have a 5 micrometer or 10 micrometer window, and I want to go deep inside, like I'm drilling a large trench, for example. This is my silicon wafer, and I have some oxide, and this window, let's say, is a 50, for example, micrometer, very small. If I use TMH, it will close very quickly, but I want to drill it something like that for a reason, okay? And how I can achieve it? Because if I use a regular rectified etching, the process is fine. You can start etching at maybe 50 nanometer per minute. You can go on and on for a long period of time, but then you start also seeing polymer deposition, and that creates a problem, because then you cannot really etch deep inside the silicon. So there are different ways how you can achieve the vertical etching. The one very straightforward, as we discussed, that you can increase the time, right? You can lower the chamber pressure, means then you have more mean free path for the ionized gases to actually go, and instead of hitting other molecules, they will go deep inside at low pressure. They can go straight on your surface, and you can start etching it. You can also use ion bombardment, means you can use the ions, and the ions will hit the surface, and in that way you can do very directional etching. But then again, when the features are high aspect ratios, it means tall and less wide. In that case, after a certain time in the plasma chamber, you also have some debris and carbon deposition and all that, so which creates a problem. Basically, it's a polymerization, carbon-based deposition of the materials. For that, people have developed another method. It's called the DRIE. It's a deep etching, deep rectified etching. It's also called deep RIE, and it is used actually to make structures which are high aspect ratios. In deep rectified etching, you use a plasma, which is fine. You can use a plasma also in normal RIE, but use a cycle of etching and polymer deposition. So instead of polymer to start depositing by itself, so what they do is they, in order to make vertical lines, they deposit polymer intentionally. So how it works is, you first do etching, some rectified etching, maybe with the ions also, and then you have this structure, right? So you start making this structure, and then you might then the process will start getting slow, and it's also etching on the sides. Then you do a polymer deposition, the second round, passivation layer, a thin layer of a carbonated polymer. You make a polymer layer, then you do just ion bombardment. Ion will go and hit on the straight surface, not on the side. So in that way you can now do, after ion bombardment, do a second cycle of etching. So in that way you can go deeper and deeper. You can have features which are 50 aspect ratio or 100 aspect ratio, let's say 1 micrometer wide or 5 micrometer wide and maybe 50 micrometer deep or even further. So you can have a very, very nice feature. So this is a very good technique, by the way. And it has been used in a lot of different applications. You can find tons of applications where we might need to use this kind of technique. By the way, for this one, we already went through it, right? So I may not spend time on this one, but I also uploaded a paper, so you might have went through the article. And there was another paper also which I uploaded about nanopores, where we have used anisotropic etching. So if you have done that, that's good. If not, maybe you still have time to go through it, because we will be very quickly approaching our key paper reviews. Okay, soon. Hopefully on Thursday, I'll be talking about it and give you some time to propose the topic. Not really, you really have to find one article only, basically, which should be a key paper. We'll talk more about it, but the thing is, the time is not now coming, so you should make sure that you start reading articles and all that, okay, so that you have some idea what kind of things I can do. So basically this topic will be very broad. You can use any of the sensors, all of the things which we have covered very briefly or very thoroughly in class. You can talk about it. Whatever we have covered a little bit more thoroughly, that's not a good key paper topic, because that's already covered, right? So we should choose something which we have touched and not covered, or something which we have not touched so far. And you should be able to, as a master's or undergrad senior student, should be able to actually read an article and explain it to the students. I'll give you more suggestions later on how to find a key paper, because it's not just any article. It should be the article which proposed or showed for the first time some certain phenomena, mechanism, method, or process. So we will go through it, but I'm just giving you a heads up. Okay, solid state fabrication. Okay, in solid state fabrication, we actually have so far we have learned how we can remove a material from the surface, which is etching. But sometimes we have to also deposit material on the surface. Not sometime, actually, quite a few times, almost every time we have to deposit material on the surface. And let's say if you are making gold particles. If you're making gold electrodes or any other electrodes, people who are working in the neuroscience or neuroengineering, they record the brain activity, right? So for that they use actually electrodes. Electrodes, they can measure the electrical signals. Okay, so you really have to put electrodes inside, and you can also measure the electrodes. You can put electrodes on the surface, and you can measure the conductivity of the sweat or maybe something else. It's up to you how you want to use it. But in neuroengineering, it's very commonly used definitely for looking at the different signals, how if someone has a Parkinson's disease and all that, if it is related with their brain activity or not. Because neurons generate electrical signals, right? So you can sense them. So for that, one field, very important field, is actually to design a very small size biocompatible electrodes, which can go inside the brain for mostly experimental right now. So we do need to actually deposit material. If you remember, have you seen any of you the glucose meter strips? The glucose meter strips, which are used to measure sugar level of glucose in a plasma. Have you seen that? Any one of you? So in strips, you might have seen there are electrodes on the surface, right? Very small electrodes. So we can use actually photolithography to make those electrodes, many of them. You can take a plastic sheet. You can design your mask as like what kind of electrodes you need, 2 or 3, what should be their dimensions, and print it with the photolithography. Very easily. Their sizes are larger, so it will be very easy to print them. Excuse me. I think I have to take some water. Give you just 2 minutes break. I'll be back. So with those, actually you can print electrodes on the surface, and then you have to deposit some material to make electrodes. After you design features, then you have to deposit some material which is conductive, and for that we need a process which is called deposition. Okay, metal deposition or silicon dioxide. Even in a semiconductor industry, we deposit a lot of materials on the surface. It can be silicon dioxide, silicon nitride. We can deposit also gold, aluminum, chrome, silver on the surface. Okay, for different purposes. Do you know? Any of you familiar with the solar cells? Have you ever heard about solar cells? Right. Maybe as an assignment, you should just look at the structure of a solar cells. You will see that there are electrodes there also, quite a few. Okay, which are used for energy conversion. Okay, so let's look at the deposition process itself, and later on you will see that people actually grow carbon nanotubes and other graphene also. You can use these deposition processes, some modified forms, to grow those nanomaterials on the surface. The basic idea about the deposition stage or furnaces stage is very similar. It's just a different chemicals, materials, and conditions which are used for different materials growth. So first is just a deposition. So in deposition, we can deposit, let's say, silicon dioxide on the surface. Let's take a simple example. But so far we have learned that we can use oxidation, right? If we need a silicon dioxide, we can use oxidation to grow silicon dioxide on the surface. Then, can you tell me a situation where we cannot use oxidation for growing silicon dioxide, and we need a silicon dioxide there? Let's say if we have a surface which has a metal on the surface, okay? That's all covered with the chrome. And now we want to have a very thin layer of a glass, which is silicon dioxide, for a reason, to insulate that bottom layer with the top layer. So can we grow silicon dioxide there with the oxidation? If we have a wafer which is covered with the chrome, and now we want a layer of silicon dioxide on the surface to insulate it from the top materials, with whatever we'll be depositing. So can we use just oxidation, right, to have silicon dioxide on the surface? Yes or no? No? Okay, one answer is no. I will not ask you how, but at least say yes or no. So can we use oxidation? The question is, can we use oxidation to have silicon dioxide on the surface of a chrome? No? Okay, 2 no's, 3 no, 4. Just say it, one word. Okay, so you're not sure. Okay, that's fine. I think for what's the precondition for oxidation? You need what materials you want? You need oxygen and silicon. So silicon has to be there. If there is no silicon, if there is a chrome or other material, not silicon, then we cannot have silicon dioxide. We cannot by oxidation process, right? So if we have a surface where we have a metal or other materials or anything else, then we cannot have a silicon dioxide there with the oxidation process. In that case, but we still need that, so we use some other processes to actually deposit silicon dioxide, and that one process is called CVD. It's called the chemical vapor deposition. So in that case, you actually use gases as precursors or sources of a silicon and oxygen. So for example, in this case, and we need that at quite a few different places in many different areas. So in this case, let's say we use a SiH2Cl2 plus 2NO2. And after reaction, you will have a silicon dioxide deposition on the surface with some HCl gases, vapors will be produced, and some nitrogen will be produced that will evaporate. So you can have silicon dioxide actually getting deposited on many materials. Doesn't matter if you have a silicon on the surface or not, because you're bringing silicon precursor in a gaseous form. Okay. Then in CVD is a chemical vapor deposition. So basically you have fumes or precursor gases which reacts on the surface, and you have a thin layer deposited after reaction. But those two gases will not react all of sudden by itself. So basically you have to normally provide them enough energy so they can start reacting. Okay? So in a CVD, the energy can be provided with the temperature, right? So, and again, if you do the CVD process in an air environment, regular air furnace, it will not be good, because in air you have a lot of debris, other gases, they will also start reacting with your layer. So the layer which will be depositing will not be enough. So one thing, we have to have a chamber which operates at a very high vacuum, okay, low pressure. So very high vacuum, that's one condition. Then second, to have a good quality film, and second, you have to provide them enough energy so that they can react. And how we can provide energy? The easiest way is temperature. So there is one method, one type of a CVD process very commonly used called the LPCVD. It's called low pressure CVD, very commonly used. And in this case, we can grow actually silicon dioxide, polycrystalline silicon, silicon nitride, and many other materials. So basically you bring silicon containing gases in a reaction tube which already have very low chamber pressure, and then you provide them a temperature about 600 to 800, 900 degrees centigrade. So they react, and then they start depositing silicon dioxide on the surface. So this process makes a very, very nice film on the surface. Okay, very good crystal quality. Now the question is, if we have a metal on the surface, as in, there may be some situations where we may have a metal on the surface and we want to deposit, let's say, silicon dioxide with the LPCVD process, and the temperature required, let's say we want to deposit silicon nitride, for example, with the LPCVD process, and the temperature required for that is, let's say, about 800 degrees centigrade. The metals normally have not a very high melting temperatures. For example, aluminum is compared to insulators. So aluminum is about 600 degrees centigrade, okay, 660. So if you have aluminum, which is very, very common materials previously used to make electrodes on the surface and still being utilized in solar cells and all that. So you have aluminum which has a melting temperature of 660 or 600 degrees centigrade, and you can performing another process to deposit silicon nitride on the surface which is 800 degrees centigrade. It will not work, because at 800 your aluminum will be melted, right? So how you can deposit material on the melted surface? If you have made electrodes, they will be spread all over the surface. So, but it gives you a very nice silicon nitride at least. So in order to, then how we can bring the temperature down? So normally how we make things more reactive. So one is the temperature, right? And normally at high temperatures, things are more reactive in gaseous form. So what other way we can provide them energy? Pressure actually makes the whole process more cleaner, but it doesn't really provide them energy in a process. So that it makes, in a low pressure, what we do is normally we pump the air out, so it will generate a very low pressure, low vacuum. So then the things can react very easily. So that might improve a little bit reaction rate, but not bring more energy to the reaction overall. That is normally done with the temperature, and temperature is one. Any other thing? We can use maybe another energy source, let's say electromagnetic waves, huh? Oxygen, not really, it depends on the reaction. But we can use a plasma, we can generate a plasma with another, let's say radio frequency. If we use a radio frequency and shine a light or some other light source. For example, microwaves, right? You can use a microwave energy, not temperature, just a microwave waves will go in there, and then they will start generating plasma. So they'll make gaseous mixture more reactive in radical form. So that can, there's a second process is called the PECVD. It's called plasma enhanced CVD. So in this process, by generating a plasma, you can actually make the gases more reactive, and by doing that, actually, you can still perform the deposition process at lower temperatures. Okay, so like same thing by lower temperatures. So So in this case, you can perform the CVD process about 500 or even less than 500, like 300 or 400 degrees centigrade, like half of what we can, what we have to use in LPCVD process. But the film quality in the PCVD is not that great, okay, as compared to LPCVD. And the density of, because you are depositing at a high rate, so you don't get a very good density of the film which we are depositing, but overall it's a very nice technique actually, especially when you have something on the surface which has low melting temperature. Okay, so if I ask you to which process is better, so the answer would be based on where we are using it. If the core purpose of if our core purpose is actually deposit some material which should be very, very high quality, then I will definitely, and there are no other conditions, I'll definitely go with the LPCVD, because LPCVD gives you very good quality films, very dense and a good crystal form. The deposition rates in LPCVD are low, about 20 angstroms per minute. I would say about 2 to 3 nanometer per minute, very low deposition rates, 2 to 3 nanometer per minute in the case of LPCVD. In case of PECVD, we can have actually much higher deposition rates, about 100 nanometer per minute, okay, about 50 times more than what you can achieve with LPCVD, because the gases are more reactive in a plasma enhanced environment. And then, but the film quality is not that great. Okay, the third difference is the temperature requirement, which is actually one major difference. In temperature requirement, which requires a high temperature? LPCVD, okay, and temperature range is about 600 to 800 degrees centigrade. In PECVD, it's about 250 to 400 degrees centigrade based on different gases. So let's look at some tables which can give you some information which already people have done that. So you can see from the top silicon nitride, polysilicon, amorphous silicon, silicon oxide, doped silicon. Let's move on. Silicon carbide, which is also very commonly used in many different structures nowadays. Polycrystalline diamonds, amorphous diamond-like carbon, tungsten, and tin dioxide. All these materials can be deposited with LPCVD or PECVD. And you can see, for example, let's take a simple example. Let's take example of silicon dioxide. With the PECVD, the requirement is 200 to 350, right? 200 to 350. With the LPCVD, the requirement goes to temperature requirement is 650 to 750, or different other gas sources you require actually 850 to 900. So it's much higher temperature. But if you, there's a third one actually also, which we have not covered. APCVD. A stands for, P stands for definitely, okay, I'll give you one hint. So P is pressure, CVD is chemical vapor deposition, and A is atmospheric pressure. Okay, so that process we perform at normally atmospheric pressure. There is no plasma generation, but it's a high vacuum, high process vacuum. So you end up actually, you can still achieve depositions many cases at low temperatures, but the step coverage and quality of film is not very good. So that's why we prefer normally PECVD over APCVD. Okay. So, but PECVD and LPCVD are most commonly used, and you can think about all different, and these are gaseous precursors which are used, so you don't have to memorize anything except what we are discussing right now. You don't have to memorize if we are depositing silicon dioxide, what gases should I need to use. The table is there, you can always look at the table, and I will not ask you a question about it, okay? But if I ask you a question that, okay, can you please choose an option of gases which can be used for silicon dioxide deposition in an LPCVD process, for example. And I gave you options. In one option I will give you SiH4, and I give you SiH4, and I give you SiH4 plus O2 and SiH4 plus NO2, for example, right? So you should be able to point out easily that definitely SiH4, only one gas cannot be used to make silicon dioxide because there is no oxygen source there. It's just SiH4. So most probably you can deposit silicon on the surface with that, or you bring oxygen from some other source, right? So that kind of understanding you should have it, but you don't have to really memorize, okay, what formulas are used, okay? So, and if I ask you which process is a high temperature process, you should know. Which process normally deposit high quality film, you should know. Which process has a higher deposition rates, you should know. And which is that, by the way? Which process has high deposition rate, LPCVD or PECVD? PECVD has a high deposition rates, right? 50 times more than the other one. Okay, so this is a chemical vapor deposition, very commonly used method in a lot of different techniques. The other method is called the physical vapor deposition. Again, very common, and physical vapor deposition is mostly used for depositing metals on the surface. So if you look at the previous table, you don't see actually metals there, right, in CVD processes. Tungsten is a metal, by the way, but not gold, not other aluminum, silver, copper, or other materials, tin, chrome. So those are also metals. So these processes are not very commonly used for metal deposition. For metal deposition, we normally go with a physical vapor deposition. It's very clear from the name that we physically, there is no chemical reaction, so we physically actually deposit material on the surface. So again, you have a chamber which has a high vacuum. That's kind of a requirement for all these processes. And after that, so there are two types of physical vapor deposition. So one is thermal evaporation process. So you use the temperature actually to melt your material and make vapors, and then those vapors will evaporate, and then you have your substrate where you want to deposit a film on the top. So these vapors will go and bind on the top surface and start depositing. Okay. Sometimes you have to use some other adhesive layer to promote the adhesion, but normally these vapors stick very well with most of the substrates which we use, and just like silicon dioxide, they normally glass slide or any other, let's say, plastic sheet. So they stick pretty well. So this is very simple and straightforward. So we normally, how we can provide a high temperature here, we use voltage current relationship. So if you provide a very high voltage across two terminals, and then you have let's say this is gold or what? Okay, this is general process. Let's say you have a silver in there, or aluminum, for example. Aluminum melting with 660. So you keep on increasing voltage and currents. So that current, when the current passes through the metal, okay, at a very high current, it will produce a lot of heat also, even in the metals. So that heating, like we have a heating in the bulb, right? Okay, no, it's not. It doesn't. The current doesn't pass through the metal. Actually, we have a strip under the metal on which we load our sample. So that is heated up, and that's the insulator. So you apply very high voltage, current passes through it, like we have a heating from the light bulbs, and that is used to generate actually a high heat, high temperatures, and then you can control the temperature by changing the current conditions. And you can really very well control temperatures. I've used this equipment, and that melts the material. And then you also have a sensor inside a furnace which tells you, okay, start melting now, and you are having film depositing on the surface. Let me show you some images. Let me see if we can find one. A physical vapor deposition. Okay, for example, this is a gold palette which can be used as a source. You can put it there in a board, and like this. So this is already loaded, right? So then you apply a very high voltage and current across these two terminals, and then it will heat up this whole thing and it will start evaporating. Okay. So gold is expensive, by the way. We can let's look at now the cheaper version. So this is aluminum, but why I don't see the palette? Okay. Yeah, like these. So these are used for aluminum deposition. You can get that and put it in the boat, install it and start depositing material on the surface. Okay. So yeah, I was reading actually one news channel online yesterday, Local 10. It's at WPLG.com. It's a Miami-based, I think, news station, and they were reporting a case where I think in a Key West there is a museum. I never visited that, but there was a big bar of gold which they have preserved, and it has some historical importance. That I think there was some ship for a few years back, and it was a part of that ship which was made up of gold, so they somehow recovered it and then they put it in a museum for people to look at. And they made it such that you can, the showcase is such that you can put your hand inside. Okay, and it's like a small opening. You can put your hands in and you can grab the gold rod and you can actually feel it. And that was the purpose of doing it. But someone actually managed to take it with them somehow. But it was, and then there were two people actually. One was from another state, one was local. So it happened a couple of years back. It's not recent, and those people, so they have identified, definitely there will be cameras there, and they identified, okay, who these people are, but they never found those people. So yesterday, I think they found, they got both of them somehow, and they have recovered, they have not sold it. It's not that expensive, it is expensive, $550K, okay, about $500,000 for that rod. So I was expecting it to be maybe a couple of millions, but it was not, so. But anyways, it was expensive, and that it just reminds me when I look at the gold crucibles that just happened very recently. Okay, they just got captured recently, but the incident was a couple of years back, and they were on a run from a couple of years. But anyways, let's go back where we were. Okay, so we can deposit actually a lot of these metals by using a physical vapor deposition on the surface. And you can have a layer, so very good quality film, and which have a thickness, can have thickness from nanometers to several micron. Then there's another process which is again a physical vapor deposition, but it's called the E-beam evaporation. So the first one which we discussed is the thermal evaporation. The other process is E-beam evaporation. The furnaces are very similar, but normally with the E-beam we can achieve higher temperatures more efficiently as compared to thermal or voltage-based or current-based heating. So in these E-beam evaporators, you can deposit almost all those materials which are deposited with the thermal evaporation. You can use those materials also in the E-beam, same target. So what you do is you have a target here in that case. Then this is an electron beam which is guided with the electromagnetic, which is directed with the electromagnetic lenses, and then you accelerate them at a high voltage, a couple of kilovolts, so they will hit and strike the surface and impart, actually provide energy with the electron beam to the surface that will heat up locally that target, and then it will start evaporating. And when it starts evaporating, then you have a wafer somewhere there. So you'll start depositing there. If you look at this, so only heating is different. So instead of thermal heating, we are using electron beam to heat the surface. And on the top you have then the wafer where, or some substrate where you want to deposit material. But it is interesting that, okay, the important thing is also that you have to actually, the top surface is big, it's a big furnace. So instead of putting only one wafer, you can put a couple of them on the surface because you don't want to waste your material, right? So normally we coat a lot of whatever, like large area, we have maybe 10 different substrate, 20 substrate based on how big is your sample, and we can deposit all of, with the one run, deposit all of them together. And the same applies to E-beam evaporation, but the difference is only that you have you can now achieve high temperatures. There's other deposition process is called the sputtering. So sputtering is another fancy name for etching. So when we say we bombard the surface with the ions, we etch the surface. So that's a similar process which you use in actually sputtering deposition. So basically, in this case, you have a target which is, let's say you want to deposit aluminum in this case. You have an aluminum source, which will be a big pellet, and then you bombard your ions towards that source or your target, right? So it will hit the surface, and so you have to control the acceleration of the ions and choice of the ions, and based on the material which you are depositing, because you don't want to really provide enough. We don't want to provide them high acceleration or energy. So there is a possibility that they might get implanted inside your target. But we want to give them enough energy so that they can go and hit your target, deposit some energy as a heat and some energy as a mechanical energy to dislodge some molecules or some small chunks or atoms from the surface of a sputter target, and those now removed chunks will come and fall down on your wafer, which in this case will be sitting at the bottom. So in that way, so your ions are hitting the surface, removing small atoms, and then those atoms will fall down, and then they will sit on they will start making a layer on the surface. So let me show you a sputtering target, okay? It will give you a little bit feel. That is called a target, see? So in this case now we have a big targets like these, okay, which you can put it on the surface, and now these ions goes and hit the surface and start removing few atoms or a couple of atoms, and they will fall down on the surface, and you can start depositing the layer on the surface. And these are targets that they are normally expensive. Sputtered. Let me show you now. Silicon sputtered gold, for example. See, these are glass slides. So someone used it for gold-coated glass slides. So they sputtered gold. It looks like in this process, and you have very nice film. In that way, you can deposit in many other substrates. You can deposit gold or other materials by using sputtering, and also with the E-beam lithography. Okay. With the sputtering, but why someone want to do sputtering, by the way? What's the advantage we might get there? Because in E-beam we can kind of deposit many materials. So what's about if we want to deposit alloys, like two materials, and you want to have a layer which have two different, let's say, chrome and gold, for example, or silicon or some other copper together, or copper and aluminum. Aluminum and copper were very commonly used previously as alloys, because if aluminum has some electromigration problems, which we'll not discuss, but there are some issues that after certain temperature it start heating up, and then it start breaking. The electrodes start breaking in different places. So, but when we then put some copper, 4% copper or 3% copper in there to make a alloy, so then it actually helps them to reduce the electromigration issues sometimes. So, and there are alloys which are used for a lot of applications. So for that now, copper has a temperature more than 1000 degrees centigrade melting temperature, and I think 1024, and the aluminum is 660 degrees centigrade. So we cannot use those two materials in a E-beam or thermoevaporator, right? Because they have different melting temperatures. And if you want to make a lie on the surface, so then the best option may be the sputtering process, because now you can have a target which is also a lie, which may have a copper and aluminum at certain composition and ratios, and then you can use that and tweak your ion energy, and then you can actually deposit a lie material in the form of a lie on the surface. So there you have actually more control on making alloys, and that's why sometimes sputtering is preferred, but people also use sputtering for just depositing a single materials also. Okay. There is another deposition technique. It's called epitaxy. Again, it's a vapor phase deposition, and when we say epitaxy, the major difference between epitaxy, it is a CVD process, chemical vapor deposition process. It means you have a gaseous precursors which reacts on the surface and start getting deposited on the surface. But the only one major difference between the regular CVD and epitaxy is that the film which you are depositing on the surface has the same crystal structure. The film which you are depositing on the surface is the same crystal structure as the underlying film, underlying substrate. Let's say if you have a silicon, and if we deposit more silicon on the top of it, such that the deposited layer has a similar crystal structure, then it will be called epitaxy. Okay, and how we can achieve that similar crystal structure? Because you have a clean wafer, then you have if you look at the atoms, you will see that the atoms on the surface, you will have a certain orientation, how you slice them. And then you control the process conditions such that the deposited molecules will come at a certain ratio that they will start making structure. Let's say if the silicon, so new silicon will not just start depositing on the surface. So the process will slow, the new silicon atom will come and will arrange itself on the surface such that it will have a position so that it tries to fit in with the bottom crystal. Okay, so in that way you grow actually crystal, not just any amorphous film. So you just grow, it's a CVD, but you grow crystal on the top. But you cannot grow, let's say if gold, you cannot grow crystal on silicon crystal on the gold. Definitely they are different atoms, but you can grow silicon on silicon, or silicon dioxide on the top of silicon dioxide, like that. So then it will be called a epitaxial growth. You can grow carbon, by the way. If you can grow carbon, you can make a sheet of graphene, right? Or you can use this similar process to grow maybe carbon nanotube, which is again carbon in certain orientation, right? If you control the process conditions, and that's how they use actually CVD to grow carbon nanotubes on the surface. Have you ever seen carbon nanotubes? See, with the CVD process, thin film, so there is a process, we'll go through it later on, but basically with that, you can grow carbon nanotube on the surface. Very commonly used process. Yeah, this is, for example, a few carbon nanotubes. Okay? And they have to use a catalyst for that, but that's a different story. But the thing is, you can grow carbon nanotubes with these processes on the surface. Very commonly used process, which is CVD. And then there are tons of different applications where carbon nanotubes will be used, right? You name it. Nowadays, people just put them in everything and see what happens. They have good electrical properties, mechanical properties, and a lot of other properties which makes them special material. They're very small. People thinking about using carbon nanotube-based material, graphene, which is a thin layer in a bioelectronics, as a drug delivery carriers, because we did talk about nanoparticles. So these carbon nanotubes are actually nanoscale, small tubes or particles. So you can attach your drug molecules with them, and you can guide them to a certain direction. A lot of research has been done on that, and people are still looking into that. The carbon nanotubes also can be used as an imaging agent, contrast agent, right? So inside the body, and it can also be used in just regular electronics. There are some transistors, BioFETs, which are made from carbon nanotube. So their channels, so source and drain, the channel region is made up of a carbon nanotube. Okay, so you can make a transistor with the carbon nanotube. You can search it single wall carbon nanotube based transistor. You'll find it. Or you can also find single wall carbon nanotube based bio transistor, which is being used for detection purposes. Okay, so yeah, it's being. I know one of my colleague one time he was using carbon nanotubes, actually mixing them in a building construction materials and see if that improves the strength of a material. So like he was from a civil engineering department, by the way, but so they are looking into if it can improve the strength of a material in different reactions and all that. So yeah, it will have some limitations, but people are exploring it, so it will have tons of applications. So with the deposition, you can have a epitaxy, which is actually, in this case, a vapor phase deposition. For example, in this case, we are using SiCl4 plus hydrogen. So the silicon will actually get reduced on the surface. So hydrogen will make HCl, like gas, and then the silicon will start actually depositing on the surface, and it makes a very nice crystal. And there are different source gases which you can use for this purpose, and different temperature and conditions which you don't have to memorize for this course. There is another epitaxy, it's a molecular beam epitaxy. It's very similar to the evaporation process. In this one, the source material is heated, right? Like physical vapor deposition. So you heat it up at a high vacuum, they go and actually start depositing on the surface, but you control the conditions are much more controlled in the case of epitaxy. So that you want to make sure that they don't start getting deposited on the surface without aligning themselves with the bottom orientation. So that's the only thing which you want to improve. If you, let's say that if they are getting deposited very quickly, so what will happen that they will just start depositing on the surface. So they will make still the material silicon, but it will not be crystalline form. It will be more polycrystalline or more amorphous. So it means you have a small chunks which are crystalline locally, but not globally. They will not be crystalline. So let's see where we were. So this is what we have looked before, right? Let's see now we can bring in deposition also in this process. So I'm just using this as an example to build any transistor. So let's say we have a previously anti-material, we do lithography, then with the ion bombardment, we deposit different lines, you make a source and drain region, right? And then the next step is, okay, sorry, it has to be, what is this? Why I'm doing it, let me see. Okay, we put a photoresist. Then we put a mask. Okay, it will open up certain area in there. Then we remove that. So then purple, I think purple is a photoresist. Then you etch it, silicon dioxide. Okay, and now, so basically in this one, we want to make a connection here with the gold, okay, or any other metal, for example. That's whenever you have a source, drain, and gate of any transistor, you have to address them with some metal lines so that you can use them for your purpose, right? So you can apply voltage on them and you can turn them off, turn them on, like that. So but how we can use now metal lines? So metal lines, we have to actually open up a small area. Right now you can also connect actually metal with this one, okay? And so we can deposit, let's say, aluminum or chrome in this case, copper, sorry, in this case, and then you can make a metal lines with the photolithography. So, but if we don't want to actually deposit in the whole wave, the whole surface, we can again open a small area to make a small interconnect. So you will see. So first we deposit silicon dioxide there now. How we can deposit silicon dioxide? You will tell me. Oxidation or PECVD, for example. Two choices. If I want to deposit silicon dioxide here, can I use oxidation or do I need to use PECVD? Oxidation, we can still use oxidation in this process, right? Because you have a silicon source at the bottom. And we can also use a PECVD, right? PECVD, we don't really need a silicon, but still, yeah, you can still deposit silicon, it's dioxide on top of silicon with the PECVD. Then let's say after that I do lithograph, the photoresist. After the photoresist deposition, I actually put a mask on the surface, and then I exposure lithography, so the pattern will be transferred after development inside the photoresist. Now I want to transfer that pattern, this opening, inside silicon dioxide. And what chemical I can use for that? If I want to now transfer this pattern from silicon dioxide, which is this opening, and I want to actually etch silicon dioxide from this area, right? So what acid is used for silicon dioxide etching? HCl, HF, yeah, HF. Okay, we did talk about HF quite a few times, right? So it is HF, which is very commonly used for etching silicon dioxide very specifically. You can also use like dry etching, for example, to etch silicon, but it's not HCl, okay? HCl doesn't etch silicon dioxide. Okay, so then we use, let's say, HF or any other rectified etching based dry etching process to etch silicon dioxide, and then that is opening. This is opening, and now we can actually remove photoresist from there. Now this pattern is transferred inside the silicon dioxide, and then I just remove the pattern, okay, to make it more clear. Now let's say if we want to deposit aluminum, so what process you can use now for aluminum deposition? CVD. Okay. Anyone else? What process is most commonly used for metal deposition? PECVD, physical evaporation, right? Either thermal based or E-beam evaporation. So both processes are physical evaporation and more commonly used for aluminum. Let's say we use that to deposit aluminum layer on the surface, right? And now we want to, it will be covering whole surface, right? Now we want to make sure that we remove aluminum from all other areas where it doesn't need to be where we don't want it, to make it a line or electrode, right? So for that we have to do another, how I can remove material at certain locations. So first I have to define what locations I want to remove material, and how I will define that with mask and lithography, right? So I put another mask based on my own design, so a lot of masks. So then I actually expose it. Okay, so one step is missing here. What was that? Photoresist. Okay, so but now you understand, so we don't have to go through each detail. So photoresist, then mask, and then we expose this area where we don't want, for example. So with that, with the photoresist development and all that, it will be, then the photoresist will go away from this area, then we'll do the aluminum etch after that. And with the aluminum etch, you should be able to actually remove aluminum from these two sides, and only it will stay where it should be, okay, where you want it to be. And then this is just a one cross-sectional view, but on the top it looks like you can make any wires, any electrodes, or any interconnects on the surface. So this is general process for how we can actually start building a transistor or any other configuration on the surface, and semiconductors. Photovoltaic cell, for example, is also built very similarly, which is your home assignment, right? So you will look at it, the structure of photovoltaic cell, okay, how it looks like. You should be able to grasp it very easily. Just look at it, okay? And we will not be asking questions from that, but it's for your own reference. Okay, so let's look at the photolithography recap. So we can use different sources of light. We can use ultraviolet. We can use deep UV. With the deep UV, there are different laser sources. Excimer laser, which can be used. We can also go to the extreme UV, right, which will be maybe next generation lithography. But in a deep UV, deep ultraviolet range, we can achieve the feature size about 100 nanometer with these with F2 laser. But then again, we have quite a few techniques which we can use to improve the lithography. Can you tell me some techniques? Do you name some techniques which can be used to improve the resolution of, let's say if I use F2 and I can achieve 100 nanometer, okay, without doing any modifications. Now, are there any techniques which can still be used to improve the resolution further? Can you name some or explain briefly? There was one, it's called the optical proximity correction, right? Where we were making certain features a little larger, especially at the edges and corners, right? Based on the development, how it will be developed. So that ended up getting a nice feature. That improved the resolution of your printed structure, whatever you want to print. And then there was another one, phase shifting. The phase shifting, right? So we are shifting the phases between any enclosed two windows, right? So in that way, there will be the exposure will be more uniform. So you will have more exposure and less exposure because of the cancellation of the phases at the boundary. So there's phase shifter are commonly used in the masks. Those are basically expensive masks where you have a phase shifter layer. Phase shifter just put a small layer of another material which shifts the phase, slows down this light passing through it, that shifts the phase. Okay, so you ended up getting a better resolution by doing it. You can also use the immersion lithography, right? You can put oil somewhere or water between, where we have to put oil or water if we want to use immersion lithography. If we put instead of doing the whole process in air, if we put water or oil, we can improve the resolution to some extent, right? Do you know why? Because water and oil has higher index of refraction than air. Do you remember the formula which we used which is correlated with this finding? The resolution is W is directly proportional to K1 lambda over numerical aperture, and numerical aperture was n sine theta, right? So n was the index of refraction. If we use a higher material with a higher index of refraction, that will bring the minimum feature size smaller